very informative session for us yesterday, and he'll be continuing on from that point. Yes, Dr. Ashwath, I think we can start.
Yeah, thank you, sir, Shivan sir, Shivansh,
Yes, sir.
sorry,
Thank
Shivansh.
Yeah.
Yeah, a very good afternoon to all the participants. Yeah, so I think we can start. We already lost something like 8 minutes.
Yes, sir.
Okay, let me start sharing my screen. Yes. Yeah. Right. Yeah. So exactly what we were doing yesterday. Let's quickly go through it so that you people would have a connectivity, right? Yeah. So this is what we were discussing yesterday. We just got the introduction of differential equations, right? So by the way, what is the differential equation we were trying to define? It should have at least one derivative. Okay, if it is second order differential equation, then the order of the derivative must be 2. Okay, right? And the interesting things which we usually ignore or take it for granted is the differential equations. If you solve, you would not be getting a single solution, you would be getting multiple solutions. Means given differential equation can have many possible solutions. Okay, like one question has multiple answers. So that is what we saw in a simple differential equation of order 1. We just saw there are many possible solutions are existing, where the constant of integration what we get, which would dictate different solutions. You see, right? The C is the one which dictates what kind of a solutions we can have. Let's say you fix that, or you give the integral limits. In that case, you are going to have a single solution. Okay, if you are not given, in that case I will have a multiple solutions. Okay, it is completely different from any algebraic methods where we usually solve for fixed solutions, which I was showing here in the box. Okay, right? And another example also I have discussed here. Fine. So depending on the nature of the solutions, like yesterday somebody was asking, usually some people would guess differential equation solutions. Okay, so the best way to do is, if there is a differential equation which is linear, means I don't see any higher orders of y, I don't see any products of y prime or y double prime. So then I can simply say that differential equations are linear. Okay, so such differential equations you can start guessing with the exponential function or sine function, right? So these kind of solutions you can guess, and you can just check whether those functions, sine or exponential, do satisfy this differential equation or not by substituting. From there, you can just say you found some independent solutions. Okay, from the independent solutions, you can construct a particular solution, or it is also called a generic or general form of differential equation. Okay, right? So that's what I was saying here, general form of differential equation. So here for a differential equation, I guessed exponential 2x and exponential 3x as two solutions. Okay, right? So, and sometimes the constant integral constant, the C, could also be found if somebody has given me the boundary condition, the initial condition, at least initial condition y of 0 is equal to 1 is given. I can find exactly what is that C by substituting. Or if it is given at the boundary later values, then also I can find that C value. Okay, right? So there is just a minute. Yeah, I'm sorry. Yes. Yeah. So yeah, so boundary conditions, if I know, I can get the constant. Okay, right? There are different ways you can solve a differential equation. One is called the separable method, which we are actually doing unknowingly. So there is a name given to it. So that is rearranging the differential equations like terms onto one side. Okay, so y terms onto one, x terms onto one side, and then integrate if it is allowed. Okay, if it is not allowed, then we have to look for some other methods. Okay, so for a first order differential equation, if you see, right, there is no products of y prime or y double prime. So first order means no y double prime. So y is directly proportional. Yeah, Arya. Just a minute. I'm sorry. Uh, so there is a director. I got a call from our director. Yeah. So yeah. So the differential equations. Differential equations. When I just separate, solve. Okay. So this is the method. And in the case of linear equations, I can just use something called finding an integrating factor, like something which I multiplied the entire equation. So that would allow me to solve the differential equations much ease. Okay, so that also we discussed yesterday, right? And differential equations through reduction. This is a very important topic, right? So here we can reduce the higher order differential equations into uh, lower order differential equation. How it is done is, for example, if I have y double dot, I just introduce y dot or y prime as a some new variable, and y double prime would be p prime. If I introduce that, the higher order differential equation, that is here in this case second order differential equation, would reduce to first order differential equation. Okay. uh, uh, Fine. So now we will see one example. Okay, for example, if I have x is missing in a differential equation, in that case we'll introduce y prime is p and y double prime is p into dp by dy. Okay, so that is the example here discussed. Okay, and if just y itself is missing, okay, in that case this is the introduction. Just y prime is equal to p, y double prime is equal to p prime. So the example is also discussed. So it becomes much easier to solve this introduction, like introducing these changes. Okay, right? So second order differential equations with the constant coefficients, if we see, right? So a, b, c and d all are constants. Okay, so one example you can ask me where this kind of a differential equation would usually we come across. Again, any object which is moving because of some force, okay, and it is carrying some acceleration. So that kind of a differential equation is a second order differential equation. If there is a frictional force is involved, in that case the first order differential derivative also comes into the picture. Okay, so there is a small typo here, there is no 2 here. Okay, right? So this differential equation in a short form we can write like this. Okay, so there is a d is there as a constant which is not multiplied to any variable or derivative. If that d is 0, then we can call it differential equation is homogeneous. If that d is non-zero, then we call it non-homogeneous differential equations. Okay, right? So for homogeneous differential equations, like I was saying yesterday, we can guess exponential functions and then find the exact guessed solution. For example, guessed solution is exponential Rx. Then if you substitute, okay, uh, then if you substitute, you will get a quadratic equation for R, and if you solve, you would get what is the exact R. One example I gave you, okay, so where R comes out to be 1 and 4. Now, for some situations, the R can be also complex number or rational number. Okay, so accordingly you can get the solutions. Okay, for example, the complex number scenario, this is the equation. Okay, so you can use complex relations like exponential iy is equal to cos y plus I sin y wherever required. It's called Euler formula. Okay, right? So with this example we got that complex solutions. Okay, another equation, differential equation with the complex roots. Okay, now for the non-homogeneous case, how do you solve? Okay, for a non-homogeneous case, what you can do is you can find a solution first for the homogeneous part, and then you can just develop a solution for non-homogeneous part. Okay, how to do it is, okay, for example, you have the solution y naught x as a solution for the overall differential equation. Okay, overall differential equation as a solution y naught x. Okay, so usual thing is the solution for a differential equation must not change or must not deviate if I multiply by some constant. Okay, it's like we saw a solution is there, you multiply it by some c, you get another solution. Okay, so let's say I have y naught x for this entire differential equation. If the solution is multiplied by some factor of a, okay, right, and we have to get another solution by multiplying. Okay, let's check, let's take the LHS of this equation, and if we substitute, okay, right, and what you get to see is a multiplied by the LHS of the solution, okay, with the y naught in place. So what you are getting is LHS is equal to a into f. But what is RHS? RHS just f. So what is saying is a into f is equal to f, which implies a is equal to 1. So which means unless a is equal to 1, this is not going to be a solution. Okay, so that means what whatever solution I'm guessing, I'm saying y equal to y naught x is not the solution of this entire equation. It can be a solution of homogeneous part. So to have a overall equation solution, what I have to do, I have to write whatever guess solution plus homogeneous solution. right? If you y0 plus homogeneous solution a y1 plus b y2, where y1 y2 are the independent solutions of the homogeneous part, in that case I would get exactly overall solution of the entire entire equation with the f of x non-zero. Okay, so one example I just given here. If you see, let's take a differential equation like this. Okay, fine. So in this differential equation, uh, uh, if you see here, the homogeneous part I'll take first. I'll find solution for homogeneous part. What I'll do, I'll just guess. This is a differential equation, linear differential equation. Sine, cosine, or exponential functions solutions would satisfy them. This kind of equations. So I'll start with the one solution sine x, another solution cos x. Okay, I'll take a generic solution for this the entire differential equation as y naught alpha x cos x plus beta x sin x. I'm just starting with the y naught. Okay, so likewise I'm starting with y naught x. Likewise I'm just guessing here. Okay, I don't know what is alpha beta. So what I want to find what is alpha beta. Okay, let's substitute inside the differential equation y prime plus y equal to sin x. Okay, so when you just substitute and then cancel whatever is terms you will get. Okay, and you put equal to sin x, and what you get is alpha and betas are exactly what values supposed to be here. So alpha comes out to be minus 1 by 2, beta comes out to be 0. So in that case I got what is a y naught. Okay, y naught is minus half x cos x, and anyway I have a homogeneous part solution sin x and cos x, two independent solutions are there. Multiply with some constants a and b, you would get this the second part, homogeneous part. You add the overall solution plus homogeneous part, and then you would get the exact solution of this entire differential equation. Okay, so that is how one has to do in the case of non-homogeneous solutions. Another example I have given you here. Okay, you see here, first I'll find the solutions for the homogeneous part. So homogeneous generic solution is there. Okay, now I don't know what is the solution for non-homogeneous case. So let me guess the non-homogeneous solution for this equation is some polynomial of degree 2 in x. Okay, since I'm just guessing, I'm just making some approximation. Okay, so let's say the solution is alpha x square plus beta x plus gamma, where alpha, beta, gamma I don't know. I want to find those values. Okay, so when you substitute, here, okay, right, and I would just get what is the conditions of alpha, beta, and gamma. Okay, so right, so you can exactly find what is alpha, beta, gamma. Let me hide this. Alpha, beta, gamma. Knowing alpha, beta, gamma, I'll get what is yp. Okay, what is a yp, and adding a homogeneous part to the yp, I'll get overall solution. So this is how you can find even non-homogeneous differential equation solutions. Okay, right, fine. Let me go to the next part. Okay, so differential equations with variable coefficients. Okay, right, so maybe I should use my hand note. I think it, yeah, maybe I'll use the hand note. Okay, so for solving the problem I would use a hand note. Okay, in that way it is easier. So for the derivation part I would use the text. Okay, right, fine. Let's take a differential equation where coefficients are some functions of x. Okay, so these are variable coefficients. So far whatever we see, the p, q, and r are some constants. Let's say p, q, r are all functions of x. In that case, how should I approach this equation and how to solve that? Okay, let's take first a homogeneous part. Okay, ignore rx, put it 0 there and say. Okay, let's say this homogeneous part has two independent solutions. Let's say y1x, y2x. Okay, and taking the superposition of those two, okay, linear combination, I will have, let's say, generic solution for this homogeneous part. Okay, now this is looking like this, right? Okay, then I will make an assumption or a guess saying the non-homogeneous part, the entire differential equation would have something of this kind where a and b both are some functions of x. Okay, right? So that is possible. So let me call v1, v2 are functions of x. Okay, right? Now I have y naught x. Okay, exact solution of this entire equation, let's say, and let's substitute y naught x into the differential equation. Okay, when I substitute, first let me find out what is a y prime, means first derivative of y naught. Okay, so this term would give two terms. One is v prime y1, v and y1 prime, v2 prime y2, v2 and y2 prime. Okay, so there are four terms I have generated. So let me rearrange in such a fashion. The derivatives of v1, v2 are in one place, derivatives of y1 and y2 in one place. Okay, right? So now let's mandate the v1 prime y1 plus v2 prime y2 could be 0. Again, I'm making an assumption that is possible. Okay, individually v1 prime v2 prime cannot go to 0, but together they multiplied with y1 and y2 can go to 0, right? So let's put that assumption is equal to 0, and right, so if that is the if that is mandated, so what I'll have, y naught x is equal to v1 y1 prime, v2 y2 prime. Okay, right? So now, which is equal to y naught double prime. From here I'll get another two terms when I do the another differential equation, and having y naught prime, y2 y naught double prime, you substitute back in the entire differential equation. Okay, so this one and this one, if you substitute back in the entire differential equation, is this. Okay, right? So substitute back and then just do a small rearrangement. Okay, what you see is whatever is multiplying to y1, y2, sorry, v2. Okay, these two terms can send to be 0 because, okay, as per the homogeneous solution, y1 and y2 are the homogeneous solutions, which is equal to 0. So when I substitute, what I'm left with is just v1 prime y1 prime plus v2 prime y2 prime is equal to rx. Earlier I mandated, okay, I took the mandate this relation, right? So that relation, if you put back here, I get two algebraic equations with the derivatives involved. Okay, from there I can find what is the v1 prime and v2 prime. So first let's find what v1 prime in terms of v2 primes and y1 y2. Okay, substitute back into this equation and get what is v2 prime. If you carefully see, v2 prime and v1 prime are the functions of y1 y2, y1 prime y2 prime, and just rx. Okay, right? So this is the relations. Now having known v1 v2 derivatives, you can find what is the exact v1 v2. You can find the moment you know v1 v2, you can get what is the solution. Okay, so let's do a small problem. Okay, right? Okay, so let me use my hand note here. Yeah. Let me set it up. Yeah. Okay. So the differential equation which I am going to have is, okay, differential equation y double prime plus y is equal to cosec x. Cosec is 1 by sin x. Okay, right? So now if you just take homogeneous part, okay, homogeneous part can have solutions. Y1 is equal to sin x and y2 equal to cos x. Okay, two solutions are possible. Okay, so generic solution would be some a into sin x plus b into sin x. But what we want solution for this entire part. Okay, so let me say the solution of the entire part is some y naught x is equal to some v1x sin x plus v2x cos x. Okay, that is possible. Now when I make this assumption, earlier I mandated v1 prime y1 plus v2 prime y2 is equal to 0, v1 prime y1 prime plus v1 prime y2 prime is equal to rx. Okay, so as per the given solutions here, rx is cosec x. Okay, right? So cosec x, fine. So now from here, first of all, let me find out what is my from here. Let me find out what is the v1. What is y1? Y1 is sin x plus v2 prime. What is y2? Cos x is equal to 0. Okay, v1 prime. What is y1 prime? Y1 prime is just a cos x. Okay, and what is y2 prime? Y2 prime is minus cos x, so minus sin x. Okay, v2 prime sin x is equal to cosec x. Okay, right? So from here, let's find out what is v1 prime. v1 prime is minus v2 prime cos x divided by sin x. And from here, okay, in place of v1 prime, let me substitute v2 prime. v2 prime cos x divided by sin x minus v2 prime sin x is equal to, okay, 1 by sin x. Okay, right? So let's multiply throughout this entire equation by sin x. When I do it, what happens is v2 prime cos square x minus v2 prime sin square x is equal to 1. So let's take common v2 prime overall common minus sign. I'll get cos square x plus sin square x, which is 1, by the way. So what it implies? It implies v2 prime is equal to minus 1. You see? So v2 prime is minus 1 means v1 prime is minus cos x divided by sin x. Okay, see here, minus of minus, that is, it becomes plus sign. Okay, right? It's actually cot x. Now v2 prime means dv2 by dx is minus 1, which implies v2 is minus x. Okay, right? Plus some constant. And what about v1? dv1 by dx is cos x by sin x. So I can just do the integration. dv1 is equal to integration of cos x divided by sin x into dx. Okay, so if you just to try to find, v1 would be log of sin x plus some c. Okay, so now the overall solution would be, okay, what is a v1? v1 is log sin x. Let me ignore the constants. Okay, into sin x plus v, what is a v, okay, sorry, v2 is minus x, na, minus x cos x plus this is y naught x and I want to have a sin x plus b cos x. So this is a homogeneous part solution. Okay, right? So this is how you will find the solution for the differential equations with the variable coefficients. Okay, right? So let's see what else I have. Yeah. Now, okay. Now, one more thing. Now, just now we saw from the known solution generating new solution, right? So let's say I have one solution only. For example, even for if you just see uh, even for a simple homogeneous equation, let's say I have only one solution known, then I want to find another solution. Okay, so what should I do in this case? Let me say y1 is known. Let me multiply y1 with a v, where v is some function of x. Let's say I generated a new solution, right? Okay, when I substitute this y2 into this above equation, first of all, let me find out what is a y prime, y2 double prime, and then substitute back into above equation. Do the rearrangement. Earlier I said y1 is a solution of this equation, so that means this term is going to be 0. So what is left is few terms. Okay, so when I rearrange those terms, there is a v double prime involved, v prime is involved. Okay, when I just put it into the like terms onto one side and then do the integration. Okay, when I do the integration, interestingly what you see is v is going to be integration of 1 by y1 square, the known solution, exponential of minus integration of p into dx into dx. By the way, what is a p? Remember, okay, p I have to find out. Okay, right? From a given solution, I have to find out what is a p. So from the given equation, p is some expression you will have. Okay, right? So that is what you need to know. Interestingly, you see there is no q anywhere coming in the equation. Okay, right? So only p which dictates the solution of that particular equation. Okay, so knowing v, you can multiply it to the y1, you would get the next solution. Okay, so one example we'll just to do. Okay, quickly one example. Let's take this example. Okay, fine. Okay, the example is y double prime minus 4y prime plus 4y is equal to 0. Okay, so first of all, how did I earlier I was finding out the solutions of this differential equation is I'll make a approximation like y solution would be exponential rx. When I substitute, what I'll get is r square minus 4r plus 4 is equal to 0. It's quadratic equation. The solutions are only one. Okay, that means I only know one solution, so I want to find one more solution. So what is one more solution? Let me call that as some v into y1. Okay, some v of x exponential 2x, right? So what about v? As per our earlier derivation, you see here v is integration of 1 over y1 square exponential integration of p dx with a minus sign. Okay, so first of all, so let me write down integration of 1 y1 square exponential p into dx, this dx. This is what my v is. First of all, as per this equation, p is minus 4. Okay, integration of minus 4 dx is minus 4x. Okay, exponential of minus 4 dx is exponential 4x. Okay, right? So Now I will get what is v, which is okay exponential, okay, exponential 2x whole square exponential minus 4x into dx. So which is what? So exponential minus 4x, sorry, there's a minus sign, minus of minus, right? Minus of minus. Okay. So minus minus goes plus. Sorry, this is a plus plus. So this gets cancels. So what is left with is integration of dx, which is simply x. Okay. Therefore, v of x is x. So y2 is v of x into y1. So which is x into exponential 2x. So knowing y1 solution, I generated another solution using this integrating factor. Okay, right? Fine. So let me go to the next scenario. With a variable coefficient scenario, right? So one more example is given. I'm sorry. Yeah, we just got this solution. Another example here, you see. So in this example, first find out what is the p. P is 1 over x. Then integration of px dx you will find, that is the log x. Substitute that into exponential minus log x, so which is 1 by x. Then you will find a v. The moment you find a v, you multiply that to your y1. Okay. Then you get a new solution. Okay. Right. Okay, there is one more interesting method. Somebody was asking yesterday, partial differential equations, right? Okay, partial differential equations comes when involved systems are, okay, for example, it's a so for example, involved systems are functions of multiple things. Let's say functions of multiple things. Okay, by somehow a given differential equation, let's say if I just write into m into dx plus m into dy is equal to 0, sorry, n into dy. Okay, if I am able to do it, if I just express the given differential equations would be usually like this. Okay, where this is called a derivative function. Okay, if I am able to resolve the given differential equation, which is having, let's say, dy, let's say it is having both x dependency and y dependency. In that case, if I am able to write the differential equation into this form, okay, then I can do some tricks. It is called solutions using exact condition. Okay, what is that exact condition is? Where m is, okay, partial derivative of dx and n is partial derivative of dy of function f. Okay, where f is the derivative function of this differential equation. Okay, so if by any means, okay, if by any means, if dm by dy is equal to, okay, dm by dy is equal to dn by dx, if this exact relation is whole squared, then what we can show is, okay, dm by dy dm by dx is equal to dm by dy dn by dx, which is actually, so I can just interchange the derivatives, doesn't matter. Okay, I can show that. Okay, sorry, this is a if f, sorry, if this is whole squared, I can show this. Okay, right? So what it implies is f is actually a constant function. if that constant function, if this is a direct implication. Okay, the moment I know what is a f is a constant function, I can find what is dm by, okay, sorry, oh, m is df by dx na, and n is df by dy. So by knowing this is a constant, I can find what is the m, and I can find what is the n. Okay, so from there I can exactly find solutions of entire differential equation. Let's take one simple example and try to understand. Okay, let me say there is a differential equation x by 2 example, okay, cot y into dy by dx is equal to -1. So this is a differential equation I have. So I want to rearrange in such a way, I want to arrange into m into dx plus n into dy is equal to 0. So that is what I want to have. So what I will do now, let me put x cot y okay, dy is equal to minus dx. Okay, first rearrangement. Fine. So there is a cot here. Let me put this as a cos dy is equal to 2 by x sin dx. Okay, right? Fine. Yeah. Right. I want to have m and n both functions of x and y. I need to have that. That is very much required. So by just doing a rearrangement, I can do something like x cos y dy is equal to -2, okay, sin y dx. Okay, then the rearrangement 2x sin y, okay, dx plus x square cos y dy is equal to 0. Okay, now if you carefully see, my mx comma y is 2x sin y, n x comma y is x square cos y. Okay, right? So now first thing I have to find whether dm by dx is equal to dn by dy. So let's find out from here. What is the derivative of dm with uh, yeah, what is the derivative of dm with the x, which is simply 2 into sin y. Okay, right? And then what is the okay, so just a minute, dm by dy I have to find, sorry, dy, which is 2x cos, okay, cos y, right? And dn by dx I want to find, which is 2x cos y. So both are equal. So this is satisfied. Okay, when this is satisfied, what I can show is df by dx m 2x sin y. Okay, what I can show is df by dx integration is equal to integration of 2x sin y dx. Okay, if you just this integration on the left, I'll get f of x comma y is equal to, okay, 2x square by 2 sin y, okay, plus some constant I want to add. What that constant would be? The constant would be a function of, the constant would be a function of y. Okay, function of y, very important, because we have just taking integration only with x. So this is just taking coming out of the integration without being doing anything. Okay, so f of x comma y is x square sine y plus. Okay, now I know what is f x comma y, but df by dy is actually n x comma y. Now let's cross check whether I am getting from here the same. So that is 2a, so x square cos y plus y prime. Okay, and what is this exact expression from the from from the equation? From the equation, what is n? N is x square cos y. Okay, n is x square cos y. But I don't have any extra term. What it means? Extra term is 0. So extra term is 0 means which is some constant d. Okay, so f of x comma y is equal to x square sine y plus some d constant. Okay, so by the way, which is some constant, so which implies x square sine y is equal to c minus d. Let me call some constant c prime. Okay, or c tilde. Okay, and y would be sine inverse c tilde divided by x square. This is a solution. Okay, so this is how we have to find the solution for a differential equation even when there is a coefficients are some variable functions. And luckily, if I'm able to write the exact relation, if I'm able to cross check the exact relation, then I can use this technique. Okay, right? So let me go back. Okay, one more example I have, I think, here. Just a minute. Another example. So counter example is here I'm just giving. Let's say I may not able to see the relation doesn't hold. In that case, I need to look for some other method. Let's say sometimes the exact relation holds. See here in this case, the exact relation is actually holds. But the thing is, when you try and find the solution, you see it's a very complicated solution. Explicitly, you can't find y in terms of x. Okay, so it's not that every time this exact solutions can be found, but we have to look for some other technique. Okay, so this is about so far we have discussed all the differential equations of different types, right? Okay, and how to integrate them we saw. Now let's go to the numerical integration part. Okay, so numerical integration. Okay, yeah. So before going there, if there is any questions, let me see. By the way, please don't worry, and you can just see and read through my notes, and then you will understand. Okay. In programming, did we use these methods to solve differential equations? Yeah. In the programming, all these differential equation methods we would not be using. So we would be using a technique called numerical integration. Okay, right? So where we'll just discuss one by one, right? Okay, yeah. So let me quickly use my hand note and okay. So let's use a new note so that this is, yeah. So numerical integration. So the numerical integration is using programming to solve the differential equations. Okay. So first of all, let me write down what is a differential equation would look like. Okay. So let me use time derivative. That is easy. Is equal to f of y comma t. Okay. Sometimes I write to f of t comma y or y comma t, doesn't matter. So this is a derivative function. Okay. Now left hand side I have a derivative. Okay, so first of all, let's find out what is the derivative. So if I have to explicitly write the derivative, so which would be limit delta t tends to 0, y at some time divided by delta t. Okay, where delta t is okay. Oh, I am getting to same page. Where y is so delta t is okay. So derivative of t is limit delta t tends to 0. Okay, y at some tn plus 1 minus y at tn. Okay, this is happening again delta t, where delta t is tn plus 1 minus tn. Okay, right? So by the way, which is equal to f of y comma t, or f of wherever I'm substituting that. Okay, so now, so this is right. So now I can just approximate y tn plus 1 minus y tn divided by delta t is equal to f of yn tn. Okay, I'm just ignoring delta t limit tends to 0. So I'll just have to do this approximation. Okay, now if I just do this, y of tn plus 1 is equal to y at tn plus delta t into f of yn tn. So I just got an equation. It's called Euler equation or Euler's rule. Okay, what it says is if you know a value of a function at some time tn, you can get later times by multiplying, sorry, by adding some correction term delta y, which is equal to the slope at that point multiplied by small increment, okay, delta t. That is what this Euler's equation is telling. So if I just to draw a geometrical interpretation, if I take a curve like this, so let's say I know tn plus tn. Okay, let's say I know what is a yn. So I want to find at this point where tn plus 1, I want to find yn plus 1. Okay, so this is a actual curve. This is a y of t. Let's say I don't know that. Okay, for the geometrical interpretation I took it. Okay, so now I only know this value, which is yn tn. I know I want to find yn plus 1 at tn plus 1. I want to find that. So what Euler's rule is saying, you please draw a slope at this point. Okay, draw the slope, which is what? Slope is tn comma yn, or yn comma tn, doesn't matter. I'm just taking order. So slope is derivative function, right? So that is what the differential equation says. Differential equation says dy by dt is equal to f of t comma y. So if I just substitute the points coordinates, I'll get a slope at that point. So this is a slope, this is a slope. Okay, now this is slope is like this, negative slope, by the way. If this is a delta t, okay, if you multiply to the slope delta t, okay, what I'm saying, delta t multiplied by f of yn comma tn, which is delta t into slope, what I get? I'll get a increment in y. What is the increment in y? Okay, this is the increment in y. So this is delta y. Okay, so this is a point. So for a y initial value, I am going to add delta y. I'll get yn plus 1. So what is this one? This is a point yn plus 1 comma tn plus 1. Okay, so I'm getting a point at this point when I do the Euler's integration. Okay, so if I use this rule, I'm getting this point. But by the way, this is the actual equation. Actual equation. Okay, actual curve or actual curve. But the solution which I found from Euler rule is here. So there is a error, there is a correction. That correction is because of I am approximating something here, and also, right, I'm just taking the idea of multiplying the slope where step size is so large. You see, as I increase the step size, increase in the step size, the error is actually increasing. Say at this point error is small, at this point error is large, at this point error is large. So as you go away and away, the error is actually increasing. That means to avoid the error, you have to take very, very small. So that is what we have ignored in the first place. By ignoring this limiting to 0, if we do the calculation, at every time there is a correction happening. So what exactly happens in general is, let's say I have a curve like this. If you start dropping a slope and finding a point, and then dropping a slope, finding a point, and dropping a slope, finding a point, and like this, if you see, this is the actual curve, and this is what you get, like it obtained from numerical integration. Okay, so that is a problem with the problem with the Euler's rule. Okay, so for that somebody came along, his name is Kramers. So he added a correction to the numerical integration. What is that correction is? Okay, right, he said, anyway you are going to find, okay, tn plus 1. So this value, you are going to find yn plus 1, right? Okay, so this point is tn plus 1, this point is tn. Okay, so first what he said, you please go ahead and find what is the yn plus 1 as yn plus delta t into f of tn comma yn. He said, okay, you go and find out. Okay, so when you find, you call the whatever value you are going to find as per the Euler as a prime. Means it is something in between, not a derivative prime, some value other than what is the expected, because this is having some error. Now he said, please use that and drop a slope at that new point. Okay, at that new point you drop a slope. What is that slope would be at that new point is tn plus 1 comma yn plus 1 prime. Okay, now he said use that slope to again calculate the exact value yn plus delta t f of tn plus 1 comma yn plus 1 prime. Okay, so if you do this correction, he said you would be able to get some approximated solution, some better approximated than Euler. What it means geometrically is, okay, carefully if you just see, first I drop a slope. Okay, first I drop a slope. Let's say this is a slope at this point. This slope is yn comma tn. Okay, right, let's say you find a point, right? Okay, so this is yn plus 1 prime at a tn plus 1, and he's saying you find a slope at this point. By the way, there is no curve. How do I find the slope? So what you can approximate is, let's say this curve is moved slightly bottom. Geometrically, you can say that. Now you drop a slope. Okay, that slope is y. So f y n plus 1 prime comma t n plus 1. Okay. Now when you move the curve back, okay, when you move the curve back, the slope would be like this. Slope is not going to change. It is the direction is remaining the same. So this is f yn plus 1 comma tn plus 1. Okay. When I take this part and multiply delta t to that, I would get a very close to the curve. Okay. So that is what this point, this multiplying, this is a slope. For that slope, you multiply delta t and then add that new obtained correction to yn, you will get a yn. So this method of adding the extra derivative is actually called Kramer's correction to Euler. Okay, right? So this is how numerical integration is done with little bit more approximation, like a little bit more approved. Okay, right? Now, so anyway, people are using multiple slopes. Okay, so somebody called Range Kutta, so they came forward and they said, anyway, it's about playing with the slopes, right? So let's say I have a curve. Okay, so I want to find, knowing the old solution at old point. Okay, this is yn comma tn. I want to find yn plus 1 comma tn plus 1. I want to find. So what they said, what you do is use the Euler method, find a new point. Okay, just like grammar, you drop a slope there and you take that slope. So yn plus 1 prime you find using Euler method itself. Okay, using Euler method itself. Let me take this. Okay, right? So one slope here, another slope there. Okay, so this is at tn, this is at tn plus 1. Okay, so you take, first use the Euler method, find the new point using the same simple technique. Okay, and now you just to drop a slope at the new point, which is yn plus 1 prime comma tn plus 1. Okay, so you get two slopes. One slope is this, another slope is this. You take average of both of them, you use that to exactly find the solution, which is delta t into f of tn comma yn plus f of tn plus 1 comma yn plus 1 prime divided by 2. Okay, so they called delta t into f of tn comma yn as some k1, delta t into f of tn plus 1 yn plus 1 prime as k2. So which drops out to be yn plus 1 is equal to yn k1 plus k2 divided by 2. So where this is actually the average of slopes. Okay, this is the RK2 method for you. So basically what you are trying to do is just to take a curve. If I want to find a new point from the known point, you draw slopes at those 2 points. You find the average of those two slopes. So those average of those slopes would look like this, which is somewhere at the center. Okay, if you move the slope to the near to the curve, it just falls like this. Okay, right? So in that way, so the Range Kutta second order, there is a two slopes means second order. Okay, and now people are even playing with the number of slopes. Okay, so the number of slopes they're playing, they thought, why can't I increase the slopes? Okay, increase the slopes means find one slope, another slope, another slope, another slope. You take average of all the slopes, 1, 1, 2, 3, 4, average of all the 4 slopes, and use that to calculate exact solution. So that is Range Kutta fourth order. Okay, what it says is the new solution would be equal to old solution plus average of K1 to K0, K1, K2 plus K3, or you can say K1, K2, K3, K4, right? Doesn't matter. Where K0 is simply delta T slope at old point. Okay, where K1 is delta T slope at delta T by 2 comma. Okay, this is a y plus K0 by 2. Okay, K2 is delta T f Tn delta T by 2 y plus K1 by 2, and K3 is delta T f into Tn plus delta T y plus yn. Sorry, y, sorry, this is y plus K3. Okay, so what exactly K1, K2, K0, K1, K2, K3 are describing is they're describing 4 slopes, and I'm taking an average of them. Is literally just trying to find the slope of all the slopes. Okay, so that's something like looks like this, which is at the center. So that would have much more corrected solution. Okay, right? So okay, so let me go. This one we discussed. This one we discussed. Okay. Okay. So one thing is very important. What is the error in the case of Euler method? So Euler method error is, as we know, the error in the Euler method is happens at the step size, right? If you increase the step size, more error. If you decrease the step size, less error. But the problem is the step size is decreased, the number of computation time would always increase. So there is a compromise one has to do. Okay, so I have just taken one simple example and try to see what is the error creeping in the case of Euler method. Okay, so derivative function is just y itself. Okay, f of Tn yn is just simply yn, y. Okay, so let's first find out first step Euler and second step of Euler and substitute the derivative function as per the equation. Okay, when we substitute, for example, if you just take y2 in terms of y naughts, okay, very initial value, what you see is, okay, the h naught square y naught is there. But as per the Euler method, what should be y2? y2 is y naught plus the overall step size from y0 to y2, which is 2h, multiplied by old value as per the derivative function. But there is an extra thing which is being added. Because of that, there is an error occurring. So for example, here, when I do the integration, this much error is being added. Instead of getting this point, I'm getting this point. So because of that, extra error is actually happening at the order of h square y naught. If you take h is very small, this thing would going to be disappear. So in the Euler method, the step size error is at the second quadratic order. Okay, right? So this is what I was showing earlier solution. Because of Euler method, you are actually deviating away and away from the actual solution. Okay, so if you use the Cramer's correction, you go close to the actual curve. That is what discussed here. Okay. Okay, now second order RK2 method, geometrical interpretation, I just given here. Okay, this we discussed. Okay, now just a minute. Let take. Okay, so RK2 method, if you just see, this is a two slopes, then the average. The error you see, interestingly, in RK2 method, the error is happening at the order of delta 3, delta t step size cube. Okay, not at a quadratic. It is much more better than what is Euler method. So the question is, how did I give this expression is, there is a derivation which is actually requires a lot of time. So I am just adding supporting material. Okay, there I have discussed the derivation part. Okay, just a minute, let me show you. Yeah, here you see RK2 method derivation. Okay, if you use the Taylor's expansion and chain rule and all, so what you are going to get is, you are going to ignore the terms of higher order delta 3 t to the power of 3. If you ignore those terms, you would get whatever expression we are just now using. That means the error is occurring at the delta t to the power of 3 orders. Okay, so that is what I was proposing, or I was using for the discussion here. Okay, for example, let's say there are n steps in the integration. For example, in the case of Euler case, okay, how much error it is going to be creeping up if you calculate. So interestingly, it is just a delta t square, which is with the one step itself. In Euler case, delta t square error is occurring, but in the case of RK2, overall integration of n steps, overall, let's say 100 steps. Okay, even in that case, the error is much smaller than than Euler. Okay, so RK4 method I was discussing with you earlier. Okay, right? So here it's all about having multiple slopes between initial point to the later point and take their averages. Okay, so just like I was giving you a derivation here, similarly you can get the derivation for RK4 method also, which is very lengthy. Okay, so just RK2 itself, it takes a lot of effort to get a derivation, but RK4 method, again, it's very cumbersome. But anyway, you can take it for granted. This is the final equation. Okay, and compared to RK4, RK2 is tremendously improved with accuracy, because you see the error is now like decreased to the higher powers, like delta t to the power of 4. That is a fourth order step size. Okay, and overall error is also further decreased. Okay, so that is what RK4 method integration wise. Okay, so let me show a small small numerical integration. So before going there, the which problem I would be using, let me discuss that, and then I will go there. Okay, right? Okay, just a minute. Yeah, fine. Okay, let's take this example. Okay, spring mass system. If you just take, there is a spring and there is a mass. Okay, just like a free falling body, but a spring resistance is there, it goes up and down, right? So if I can write down Newton's second law and write whatever forces are there. So there is a rigid force of the spring. Okay, there is a gravity. So you can just put them together, what you can finally get a second order differential equation. Okay, let's say x is along the vertical direction. Okay, right? Or you can take the spring constant like this. Okay, like let's say you can take scenario, if you are not comfortable taking x in the vertical plane, you can just take, let's say there is a horizontal plane, frictionless plane, there is a mass, there is a spring. Okay, right, spring constant k, and then I just move it in the x direction. Okay, when I move it, because of the string constant, it moves and makes a oscillations like this. Okay, right? So in that scenario, this is a equation. Now it's a higher order differential equation, right? So what I will do, I'll just introduce the differential. Let me write down the differential equation. Take the differential equation. Okay. So d doubles is equal to, okay, k by m into x minus t. This is a differential equation. What I do is, the second order differential equation, I will introduce dx by dt is equal to v. I want to reduce second order differential equation to first order differential equation. Okay, when I introduce that, what happens? This would become dv by dt is equal to k by m x minus g. Okay, so I have one equation dx by dt, another equation like that. So let me introduce new variable y. Let's say there is a vector y. Okay, vector is having two functional values. One is x and v. Okay, so what I do, derivative of that vector is equal to some v comma x. Okay, so what I mean by that is, there is a vector x comma v is equal to, okay, right? So d by dt is dx by dt is v, dv by dt is k by m into x comma g. This is what I have. Okay, right? Now this is, by the way, it's first order differential equation. So first order differential equation, I can solve it using Euler method. Okay, what is that is yn plus 1 is equal to yn plus delta t f at tn comma yn. Okay, where y's are vectors, not two-dimensional vectors. Y is having two variables. One is x, another is v. Okay, so now let's take and try to integrate it and see whether the solutions are correct or not. Okay, let me exit this presentation here and use my another system. Okay, I'm sorry, did I lose my presentation? Yeah, I'm sorry, I lost the presentation. Okay, let me quickly share entire screen and explain and then get back to. Okay, what I was talking is this one. Okay, so I have a spring mass system. Okay, there was second order differential equation. I introduced new variable v. After that, I simplified second order differential equation to two first order differential equations and defined new variable y vector having x and v. Okay, so then I got a differential equation in the form of vectors. Okay, where y is this, where y vector, and this is a f vector. Okay, now I am going to use Euler method and I am going to use plus some Kramer's correction, and also I am going to use RK2, and also I am going to use RK4. Okay, so let me show you the integration using some numerical technique. Okay, let me share my screen here. Okay, right, so this is a spring mass system. Okay, spring mass system, let me go to the just a spring mass system, right? So what you can see on the left, let me increase the font a little bit. Okay, right, if you see now, okay, So I have given some initial values. Spring, let's say system is, the position is 0, right? So x is 0. So let's say system is at 0 position, and initial velocity is also, let's say, 0, right? Okay. Y 0 comma 0 is x, y 0 comma 1 is v. Okay, right? Fine. So now I have given initial conditions for the velocity as well as the position, and I will take the total integration time is 25. The step size is 25 by some n, where n is, let's say, 5000 steps I'll take. So there's a 5000 iterations, and step size is 25 by 5000. It's very, very small step size. Okay. So I create a time span or a line space for a given time, 0 to 25. Okay. So you can create, and for every point I'm trying to calculate what is the new value. Okay, let's say I know y value initially. So initially y value is, this is the first argument is time. Okay, so the initial value is given. Okay, I'll use the step size multiplied to that and use the derivative function, and derivative function I want to substitute what is a y value and t value into it. So derivative function is called a derived spring. Okay, so as per the Python derived spring, I have derived spring equation. Okay, so I will call a derived spring from my tools. Okay, right, let me show you my tools, just a minute. Tools, from tools. Okay, just a minute. EFGS PQRS tools. Okay, right. So derived spring. Okay, yeah, here it is. Let me increase the size of okay. So spring constant is there, mass is there, gravity is there, initial value it takes. Okay, so there is a input value comes as a state 1 and state 0 and 1, and those things are used as per the equation. It gives me the derivative function. Okay, derivative vector. So that derivative vector goes back into my spring constant. Okay, spring mass system. Okay, so the derived spring would come, and that is actually the derivative function, and it will calculate me the new value. So once I get the new value, I'll go and store it somewhere as x data and v data, the position and the velocity, and at the same time I'll just go and redo the iteration and get the new point. So I'll do that for 5000 steps, and stored in x data and y data, and I will just plot x data and y data, v data, velocity. Okay, so let me integrate this and see. Okay, so this is what you see. It's like a differential equations is second order differential equation. I'm getting sine and cosine solutions. Okay, position is red color and v is the velocity. You see it is making oscillations. Okay, it's going back and forth. The mass is going back and forth. Now there is an interesting thing here. You see here the oscillations are increasing. Okay, the amplitude is increasing. Can anybody point out, is it okay, the spring mass system, the oscillation amplitude can increase? Somebody? Okay, yeah, I will definitely share the code, don't worry. Okay, so can anybody point out the oscillations can increase? Somebody is saying no, it should decrease. Absolutely, right? So the energy is consumed. Okay, even though I say frictionless, so it, because of rigidity, it should decrease. Because of the errors in the Euler integration, what I'm saying oscillations are increasing. Okay, that is wrong. So what I do now, let's add a Kramer's correction to that. What is the Kramer's correction is, take the new point, find the slope there, again use that and calculate the new point. So that is what the Kramer's correction is. Okay, Okay, so this is a Cramer's corrected code. The code is same, only these extra 2 steps are added. Okay, what is that is, take the new point and find the derivative at that new point and use that derivative to calculate the new point, corrected new point, and you use that and redo that iterations continuously. Okay, so let me integrate now. Yeah, now you see the amplitudes are decreasing. If I increase the number of integrations, so number of iterations, let me increase. As of now it is 10,000. Okay, so let me increase this to maybe number of iterations 10,000 right now. Let me increase that to 20,000. Okay, just increasing. Okay, no, that increasing is not going to help me. I want to integrate for a larger time. Na? So let's take 50. Yeah, you see now? So oscillations are decreasing. If you go further and further, let's take 100 integration time. So oscillations would die down. See, you see here? Okay. Oscillations are dying down. Okay. If I don't use that, for example, if I don't use these 2 lines, okay, and then let me comment those 2 lines, comment, okay, and this is without Cramer's correction. If I integrate, see, it is giving opposite. The amplitude are increasing. Okay, so that is not the case. The errors are because I am actually going away, iterations are going away from the actual curve because of Euler correction. Okay, right? So this is one. You can also use, instead of Euler, you could use RK2 method. Okay, right? Let me go. Okay, let me save this. Okay, right? So derive spring. You can use RK4 method or RK2 method or any method if you want, and then you can find the exact solutions. Okay, so instead of Euler, I have written a code like that. I can just simply replace RK2, RK4 or RK, any of these methods. Okay, fine. Yeah. So if let's say I have everything actually set up. So let me refresh it. Yeah. So for a numerical integration, so I have added this entire detail of numerical integration. You see here, okay. For this is the actual curve. If I do Euler method, actually I'm deviating away. If I use the Cramer correction, I will come very close. Okay. If I use RK2, I'll come very, very, very close. If I do RK4, I'll get exactly. You can just integrate any particular equation, okay, and then try to see that. So the code is also explained. Okay, the programs I will share, right? So explicitly I just explained what is my derivative function, what is the Euler function. Okay, so the program is explained here, what is each step is doing. Okay, right? And you can also compare Euler with RK2. Okay, right? So this is a free falling body scenario, right? So this example we just discussed, amplitude is increasing, which is wrong. If I do the correction, amplitude would decrease. If I use RK2 method, it is a much more effective. Okay, and the derivation, like I said earlier, we have a derivation for the RK2. Okay, so which is simply equal to having 2 average of 2 slopes and using that to find the correction term. Okay, in fact, it is also equal to find a center point for the 2 times two temporal locations and draw a slope at that point. Even that is also holds good for RK2 method. So even that discussion is given here. Okay. So I'm not getting into the details. You can just go through. It is neatly explained. Okay. Right. Okay. So the fourth order or Runge-Kutta method I just discussed. Now I just want to tell you what is that four slopes. Okay. Right. So the first slope would be initial point. Second slope would be the next point. Okay. Right. At this point, next slope. And the third slope would be at this point. Okay. See here. Right. Using the previous slope, I'll get the next slope. So you take average of all of them, you get the most corrected solution. Okay. Right. Now, this is all integration, numerical integration. Okay. So let me use my hand note. Okay. So let me stop presenting here. Fine. So share. Yeah. Fine. So maybe I'll take a new page. Okay, I hope you can see my hand note. Yeah. Yeah. So now, so differentiation means what? If I have a function x comma y, I differentiate with respect to x or differentiate with respect to y. Okay. So that is what differentiation is mean, which actually telling me for a given x variation, what is the function is actually looking like. Is it going negative slope or a positive slope, or it is increasing? That is what the derivative is actually mean. Okay. So derivation implies the slope finding or calculating. Okay. Right. But what is the integration? Integration is opposite of it. Okay. So opposite of it, integration is opposite of it. So basically it is okay. Basically it is, if I have a function, let's say if I have a curve, let me take a curve like this now. So integration is nothing but finding the slope, area below the curve. If this is a curve y of t with respect to some time t, so integration is nothing but finding the slope below that curve. Now you can say, so I am having dy by dt equals some derivative function. Okay, right? Some derivative function. How do it is converted into finding a slope under the curve? Okay. For example, I have given this. I can simply get what is y of t comma y of t, right? Okay. From there, I can just have a curve and then find the area under the curve, right? Okay. Or if I am not able to find y of t, I have to somehow get the expression for y of t, and then for that expression, you can find the corresponding curve, and then okay, and then you can find the area under the curve. Okay. Now, so using numerical integration, how to do it? There is a technique called Monte Carlo integration. Okay, it's very powerful tool. Only it works in some scenarios where you know the expression of x exactly. For example, y of x is equal to sine x. Okay, so what is this function would look like? Look like this. Okay, now if I want to find area under this first half, what you can do is just enclose this into a box. Let's say box area is a into b. Okay, area of the box is A into B. Okay, and you between, let's say this is X, this is Y, between X0 to A, Y0 to B, you get random points. Okay, get random variables or random points. Okay, random points means just points, and those points would be uniformly distributed. Okay, they should not be biased, uniformly distributed. Okay, they should not be biased, not biased. Okay, if that is the case, what interesting thing I'll get is, so the number of points falling within, let's say, let me call the number of points within are some X, represented by some X, falling outside is some, let's say, ovals. Okay, okay, right? Let's say overall number of points, let's say overall number of points is capital N. The number of points falling within is N, small n. So what is the interesting thing is the ratio of number of points falling within the region divided by overall number is proportional to the area of the curve, area under the curve divided by overall area A into B. Okay, right? So area of the curve I can simply get as AB multiplied by N into N. Okay, so just by getting a random numbers, putting within the, or for, let's say picking within this required known region, and I'll just check how many points falling within the curve or how many points falling outside the curve. Okay, it's just a simply like just if statement. Okay, if some random value, if I get X random, Y random, okay, Y random, okay, I picked X random and Y random. If X random and Y random, right? So what is the X value? X value can be anything. The Y value has to be within this curve. Means what is a Y? Y is sin X. Okay, so if the Y value is falling below the sin X, I'll count it for the N. If not, I'll not count. Okay, that's a if condition. If condition. So in that way, what I will do is I use this Monte Carlo integration. You can get much more accurate solutions. Okay. Only problem here is I need to know the dimension of the system. Let's say I have a random closed curve like this. I want to find the area of this curve. Okay. So what I do, I just enclose that within a box of length A and breadth B. Okay, now I'll drop a points throughout. Whenever the points falling within this closed surface, I'll count it for N, and otherwise I'll leave it. Overall points is capital N is equal to or proportional to the area of the curve divided by A to B. So area of the curve is N by N into AB. Okay, since it's a proportionality, I can just use the proportion to find the area of the curve. Okay, so that is what the Monte Carlo integration is all about. Okay, so yeah, I'll just come to the boundary value problem at the end. I'll show you Monte Carlo integration first, and then right. So see here, for example, if I want to find a area within the, okay, right, area within this odd shape. So let's say 200 points I picked, out of 71 falling within that. So 70 by 200 into length into breadth would give me exact area. Okay, right? So why Monte Carlo integration works? Suppose if I have the curve involves, the integration involves so many double, triple integrals. In that case, if I somehow know the curve expression, I can use this. Okay, right? Now, for example, just take known example. Let's say I want to find the area of the circle. Okay, and I will just do one quadrant. Okay, I'll pick a box where circle is within. For one quadrant, I will find, and I'll just multiply by 4. I'll get the area of the circle. Okay, the code is also explained here. The if condition, right? Okay, so if the pick point, so for the circle case, the pick point is within the radius, then I will count. Otherwise, I'll leave. Okay, the pick random point. So in this way, I'll just run this and I'll get the area of the circle. So you can also get inverted parabola, area under the parabola, using the same technique. Not only that, you can take any algebraic expression and area under that the expression curve you can find using the Monte Carlo integration. Not only that, you can also find volume. So here in the case of taking the surface, here you have to take a volume and then use the Monte Carlo integration, where the random points would be three-dimensional random points. So you can use that and calculate the volume of the volume of the any arbitrary shape. Only thing is, we should know the expression for that the volume enclosing surface. Okay, that is very, very important. So let me quickly show my integration technique. Okay, share. Yeah, I will add the codes also. Okay, so go back. Yeah, Monte Carlo circle. Right, this is my code. Okay, the same thing whatever I actually given you. See here, the if condition is within the radius. Okay, I'll count. Now let me integrate. Okay, you see here, I have taken many points. Okay, so this is a landscape picture. In that case, you are getting like an ellipse, but it's not an ellipse. It is a circle. So I'll just pick the point, and if falls within the circle, I'll plot it as a red. Otherwise, blue, just for geometrical convenience. Okay. Now, using the number of points falling within over the overall points, I'll find the area of the curve. Now, just to see, area calculated is 3.12 and the actual area is 3.14. The error is 0.02 and error percentage is 0.64%. Okay, right? If you interestingly, if you see the number of points, so here error percentage 0.64. Na? Let me decrease the number of points. Let's say 1000. Okay, let me integrate it again. See, the number of points is decreased, the error percentage is increasing. You see, so the Monte Carlo integration only works if you are going for a larger and larger number of points. Let me take for 100 points and then integrate. See the okay. So yeah, in this case, luckily the percentage of error is low. Okay, but here you can see 3.12. Right. So best thing is to have as many number of points as many. Let me take 1 lakh. Okay, so the error would be much more reduced. So 1 lakh, na? So 10,000, 13,000. Okay, it would run, I think. It would run for, okay. Meanwhile, let me start the remaining part, which I am planning for today. Okay, as it ended, no, it is in 80th. Okay. Okay. Yeah, the question, there is a question, which method is better? Depending on the scenario. There are two values. At that, what is the value of the function would look like? Okay. So if I know them, I can integrate and then find arbitrary constants also. Sometimes even the initial the derivatives also given for initial values. Okay, what is the derivative? So if I those usually they are coming up with a name. Dirichlet boundary condition is the values of the function. The values of the derivatives is called actually Newman boundary condition. Sometimes they give together first point. So for the initial point they give the function. For later points they give the derivative. It's a mixed boundary conditions. Okay. One simple example, if you just take this example we have solved. Okay, right? It's having a cos and sin x. If you substitute initial conditions, interestingly, you get trivial answers. Okay, right? So likewise, there is a different kind of scenarios you can just follow. Right? You can use separable method, or there are other functions, special function methods are there. We are not getting into there in the boundary value problems. So one example, if you just take another boundary value problem, okay, right? So if you substitute the initial values after integrating, you get exact solution. Okay, right? So this is about boundary value problem. Only difference between whatever we discussed so far is we are not talked about giving a limits of the function at a given point, or limits of the derivatives at a given point. It is not given. If it is given, then things become more certain, and that is how we find the solutions. Okay. So yeah, I would be sharing all the three. Like already yesterday's lecture notes I've added, and today's lecture notes, which is having this one. Okay, numerical integration as well as some differential equation integration technique, and also this specifically for the numerical integration I've added a separate lecture notes, which is also going to be added. So there the explicitly what should the code Python code look like. Okay, I will add the Python codes, these three, four, whichever one I was showing you: spring mass, spring grammar, and spring mass friction, Monte Carlo integration. All the four codes I will add to the yeah, tools also. It's tools very much required because the tools is the file which is having all the functions. So those things also will be added. Fine. So any questions? Quiz one time. I think Pillai sir will inform quiz one. Okay, there is a question. What if there are points on the curve? Okay, so if the points are there, well and good. Okay, so error would be less. Okay, so otherwise you would be deviating. If the points are away, you would be deviating. Okay, so whatever you are saying is, while finding a new point, if you are going close to the curve, this is the actual curve, well and good. Okay, so that is what ODEINT integration technique. I think I have mentioned somewhere. Okay, so that is the technique which is like optimization technique, which explores whether the obtained error is less or not, and it integrates further. Okay, right? ODEINT technique. Fine. So I will just stop at this point. Okay, 3:58 now. If you have any questions, please do ask me. Okay, there is a question. Okay, I removed sharing. Okay, the question is for the imports in Python code, have we installed any non-system library apart from matplotlib or numpy, etc.? No, I have not done anything other than that. You can see, right? So plot and random would directly comes with the system, the Python library. If not, you may need to add that extension, but not much. Okay. See here, nothing. Fine. So the integration part itself would take one full session, 2-hour session. Like I requested, if someday if Pillai sir can squeeze 2 hours for us, then I can explicitly show how to write a particular code, tools, and then write a derivative function, Euler function, RK2, RK4 functions, all those things I will show. Okay. So this is what discussed here in the derivative. Okay. And the line by line, what line does what is also given in my hand note. Okay, fine. So that's all from my end. Over to Pillai sir.
Am I audible? Hello.
Yes, sir, you are audible.
Yes, sir. So no more questions from the participant side. Okay.
Somebody is playing YouTube, I think.
No, actually, there is one more FDP going on. One professor is taking a session there, just close to me. Sorry. So thank you, Ashwath sir, for this very detailed and informative session. I hope the participants will appreciate some coding knowledge also, because combining the equations with an understanding of how they are behaving when they are modeled in the form of graphs, that provides a very good insight into these particular concepts. So thank you, Ashwath sir, and thank you all the participants for taking interest in this particular FDP. The quiz one is scheduled for tomorrow, and possibly it will be